Okay. So the next step of our cache organization that we will be taking up, we will look at multi-level caching. So here is a CPU. Okay, here is a CPU. There will be a L1 split cache. So L1I cache, L1D cache. Sometimes even on chip we will have one integrated cache which we call as a L2 cache, right. The L1 cache will be much smaller than the L2 cache, okay. L1 smaller than L2. By being small, my access time would be fast. So as the size of your cache increases, right, so as your size increases, your access time also increases, okay. So we keep the L1 cache very small, far enough to actually do some of the far enough to basically take the locality of reference within it. So I will have that 10% instruction, that amount of things would be there in the L1 cache. But then L2 cache would be much larger than this L1 cache. It can store large more data, okay. So this is multi-level caching. Now what will happen to AMAT? AMAT will be, again I will take one instruction. So take any instruction, L1 hit means it is going to get level 1 C1 access time. If L1 miss means L1 miss plus L2 hit, essentially it means C1 access plus C2 access. L1 miss plus L2 miss, right, there is nothing more. So this will be C1 access plus C2 access plus memory, okay. So we already saw AMAT is equal to C1 access plus 1 minus hit 1, let H1 be the hit ratio of level 1 cache into miss penalty. You have seen already this equation. So this is nothing but C1 access plus 1 minus H1 into, what is the miss penalty here? Miss penalty is the average access time for C2, right. So that will be C2 access plus 1 minus H2 hit at 2, and what is that miss penalty? Memory access. That miss penalty of level 2 cache will be the memory access, okay. Are you able to follow this? Average memory access time is C1 access plus 1 minus H1 times the miss penalty, that we have seen earlier. What is the miss penalty? That is the time required to access the L2 cache, and that will be again the same thing we can derive, C2 access plus 1 minus H2, H2 is the hit ratio for the L2 cache, into miss penalty. What is that miss penalty? This is the memory access time, what you see here. You are getting this? So when we just expand that, it will be C1 access plus C2 access minus H1 into C2 access. Sorry, actually we can write it a little more neatly. C1 access plus 1 minus H1 into C2 access plus 1 minus H1 into 1 minus H2 okay. So that you just see this is the final equation. So like this I can keep increasing my, I could have a L3 cache which is much more fatter than this and so on. So I could have a cache hierarchy. Multi-level cache essentially implies a cache hierarchy. And you can use this, what sort of equation is this? This AMAT, what sort of equation is it? Huh? You have studied discrete maths, right? First year, second semester. So what sort of equation is this? Repeatedly using it, right? What do you mean? Nah, the current.
So.
Okay, this is it. Yes.
So is H1 the ratio of the hit ratio?
Huh? It's a H1 is the hit ratio for cache level L1 cache.
So
Now do we have H1 in C1 axis or it's just C1 axis?
C1 axis.
1 into C1 axis or H1 into C1 axis?
Just C1 axis. That's what we derived, no? Just look at this orange screen. You are followed? So like this I can keep deriving it for n level caches, and then today when I look at say 128 cores I will have on a chip, right? This is a multi-core heavily populated. Then I will have multi levels of this hierarchy, right? So we have not gone into multi-core, but as of now even a single processor can have multi level of hierarchy, right? As my levels go high, your access time also increases. With this background, let us now go and slowly I will start introducing the 5th assignment of your lab. Okay, so right, how will we go? So let us see. So today I already talked about a server. What is the difference between a server and a non-server? Server is expected to do what we call as multitasking. Even desktops today do. They serve you in some sense, right? So what is multitasking? More than one process will execute at the same point of time, right? Now let us assume that there is only one CPU. What it means that more than one process will execute at the same point of time? There is only one CPU, anyway it can execute only one process at a time. What do you mean by more than one process executing at the same point of time? Huh? No, it's not illusion. So now we have to go and technically understand how this is going to happen, right? An execution of a process comprises two things. One is the compute, another, yeah, I just realized. This is okay, right? Another is one is the compute, another is I/O. Right? If you take any program now, there will be some amount of CPU they will use, and then they will start using lot of I/O. And the I/O is I/O. Okay, since it takes lot of time compared to the computation time. Okay, so let us take a typical process. Right, this is the time axis, and I say, let me say red means it is compute, and this is red means compute, and some blue means I/O. Okay, so sorry, right. So I will start with red, a bit of red, then lot of blues, then again a bit of red. Then again lot of blue, then a bit of red, and so on. Okay. Now this is, say, let me say that this is some P1. Okay. Now we will do P2. So this red is called a compute burst. This blue is the I/O burst. I do lot of computation suddenly, then I do lot of IO, then some lot of computation. Okay. And by the time you press the key, so which is the most highly respected peripheral in your system? The keyboard, right? Because there only you can put Control C and stop the system. If you don't have the keyboard, the system is completely out of your control. Okay, so keyboard gets a non-maskable interrupt. Okay, so it is the slowest of the peripheral is the most important. Okay, now by the time I press a key, I could execute some 10 million instructions. Right? And sometimes you start searching where A, B, C, D. You keep on using mobile and suddenly start using this keyboard, you don't know where is A, B, C, D. Okay? The time you search and then some 10, 20 million instructions can happen. So IO is much slower. So as a process P1, I do my compute burst, and while I am doing my IO, process P2 can do its, process P2 can do its compute burst. By that, and then it will go to its IO burst. So it will start doing its IO burst. Then process P3 can do its control burst. Then it will start doing its IO burst. So by the time process 1 finishes its IO activities, several other processes can keep doing their compute. Right? So what happens in one time quantum, when P1 has done something and it's doing IO, so perceptibly I will seeing some IO is happening. So P1 is also executing, at the time P2 will also execute, P3 will also execute. Correct? So since I have an interleaving or whatever alternating sequence of CPU and IO burst, and the IO burst is much time consuming than the CPU burst, by the time a process finishes its CPU burst, the next time it needs the CPU burst, by that in that time it will be doing IO, right? By the time it needs the CPU again, before the time interval from where it used the CPU, that is between this red wala and this red wala, it started at T1, it released the CPU at T1, by the time, let me say it wants to set in T2, between this T2 minus T1 interval, several other processes can basically work on the CPU and do it. You are getting what I am trying to say? Yes or no? Huh? Right? So what happens in practice, P1 is continuously executing, P2 is also continuously executing. P1 did something, then it was waiting for IO. The moment from a CPU perspective, it's not making P1 wait. It did something for P1, then it started working on its IO burst. By the time it come back, it was ready. And in that meanwhile, when it was doing the IO, this fellow was basically doing some sensible computation with P2, P3, etc. So what are we doing here? We are merging the compute and the communication. We are hiding the communication below the compute or hiding the compute below the communication, whichever you want to call it, right? And we exploit the property that communication and peripherals involved in communication are much slower than the CPU. We make this as a point. Are you getting this? Okay. So with this as a background, let us now start moving to the next step on how this is going to be feasible. So can you please?
Can two IO devices operate at the same time?
It can in some principle. If I could have if it is going to be just with memory, then it has to wait for the bus.
Memory matter.
Yeah.
Current.
It has to wait for the bus. But then what happens is we'll talk about it. So this question you reserve, okay? So now let us go. So let us list how are we going to implement this. I assume there is only one CPU. How am I going to implement this whole thing? It is something. So let me just tell you. The first word is round robin scheduling. Okay, I think I talked about round robin scheduling sometime in the previous. I forgot what I taught you that time, how deep I went, but let me just revise it. So what are we doing here on the round robin scheduling? We are some time quantum I give for P1, then for P2, then for P3, P4, P5, again P1, P2, P3, P4, P5. So I am going on a merry-go-round, okay, one after, right? And so that's why this is called a round robin. So I equally distribute the CPU time across multiple processors. This is Robin Hood, right? That's how we got Robin there. Robin Hood used to take money from wealthy fellow and give it to each one of them equally. So that's why he called Robin, and I do it in a round, so I am called round robin. Round robin scheduling you will learn in much greater depth in your operating system course. But this is what round robin scheduling means. And the round robin basically exploits the property that there is a IO burst following every CPU burst, and the IO burst will take much larger time than the CPU burst, right. So in the same CPU, when P1 is just executed, the CPU will have enough wait time to execute P2, then P3 and P4 and P5 and again come back. Are you getting this? So this is the notion of a round robin scheduling. Now what are the questions that we need to answer? How do we go and implement this? What are the questions that are coming in your mind? We will list all those questions.
How to decide the order?
That's okay, that pinky pinky. Then after that it goes in the same order, the way it comes. Doesn't matter. How much time we allocate for each? Yes, good question. Very good question. How much time you allocate per process? Okay, the answer will be given to you in the operating system. But I should tell you, this is basically called time quantum, right? And this time quantum is basically decided based on the average CPU burst across all programs, okay, based on that. If I keep on interrupting, then if I keep on, I will give you something, stop, then give, stop, then nobody will do any constructive work. I will be spending more time in swapping you and out of it, okay. So that's how the time quantum fixing is very, very important. So there's a lot of discussion that needs to be done when we educate you on that, and the operating system course will teach you how to fix this time quantum. But I will give you an idea. Time quantum is actually fixed based on the average CPU burst of that class of programs that you see, okay. And this time quantum is programmable, right, configurable. I can change the time quantum. It's not that when I make the chip, So the operating system is responsible for fixing this time quantum. So as and when you see different profiles of people trying to access, and you see different profiles of processes, I can go and keep varying this time quantum, okay. Question number 1. There's much more fundamental question, okay. Let us say we 9 of all the first row, 9 of us are working together. Now let us say this guy is on the CPU. There's only one CPU, right? There's only one CPU. Did I teach it in the previous course? This one, this topic? No, say no anyway. Okay. So there's only one CPU, right? Now after the time quantum, let us say 2 milliseconds I give for each. After the time quantum, what should happen? He should be pulled out, and then this fellow has to be scheduled. So who will pull him out? Operating system will pull out. How can the operating system pull out? Operating system is a software. For it to do some action, it has to execute on the CPU. CPU, there is only one CPU, and he is working on that CPU. How will the operating system pull him out? So there will be a interrupt. So the most important thing for implementing this type of a thing is what? I have an timer interrupt. That is one thing which the hardware has to support. So in a computer organization course, we talk about timer interrupt in the context of operating system. correct. Now what I do to the timer, I will fix the time quantum, say 3 milliseconds, huge time quantum, 3 millisecond you can do some big yaga, okay. So 3 millisecond I am giving, I said 3 millisecond. So when I put that fellow in, I means I am the operating system, I am now executing. When I am trying to put that fellow in, I set this as 3 millisecond and say start, I push this fellow. So he starts working on the CPU. Now the hardware timer will be working, it will be down counting, and when it reaches 0, that means 3 millisecond it has been given to him, immediately it will raise an interrupt, external interrupt. Or it's internal in the sense it does not come out of pin, but it raises an interrupt, like how a divide by 0 raises an interrupt, how a segmentation overflow raises an interrupt, this fellow also will raise an interrupt. The moment that interrupt comes, what will happen? Automatically your interrupt service routine will start executing. That means automatically his program will be moved out and the instruction that will execute now will be the interrupt service routine. Who is that interrupt service routine? Operating system. So that is how in a single CPU, when one process is executing, I raise an interrupt through an external timer hardware, and I get control over it. Are you able to follow? Correct? So without this timer interrupt, this round robin is not possible. Okay. Right? You got this? Now what will happen? Now after I push him, after I pulled him out and I am pushing this fellow in, he has to start executing. What will that fellow do? His IO will be happening. So for his IO to happen independent of this fellow's execution, that means what? The CPU should not be involved in IO operation, right. The third important thing is CPU is not involved, let me say majorly, in any IO operation. If CPU is involved, it will only do that IO operation. So what sort of IO is this? We call it as DMA, direct memory access. What is direct memory access? Yesterday I explained you, we bypass the CPU. So you keep, so when he has moved out, he needs to do some IO, his peripheral, there will be some peripheral which will be talking to his memory and read and write from the memory. So all the from the peripheral, if I want to reach the CPU except for some interrupts, the way I can reach it is write into the memory and ask the CPU to read from the memory. So and when he is trying to write into the memory, he does not involve the CPU, that is why it is called direct memory access, because I am not involving the CPU here, I keep directly reading and writing from the memory, okay, right. And if DMA is not possible, he cannot do his IO, please understand. So timer interrupt is very important, DMA is very important, okay, correct. If there is no DMA, then okay. So now what happens? He was executing, timer interrupt came, it made me execute operating system, I throw that fellow out and I ask this fellow to start executing, okay. I asked him to start executing. Now when he is executing, that fellow is basically doing his IO, and that IO is happening with the peripheral and the memory. That means what? The front side bus, right, this is the CPU, this is the peripheral which our fellow wants to access, and this is RAM, CPU is also connected. Now this peripheral and RAM are talking to each other, so this bus is not free, correct, bus is not free. So if he starts executing, if his instructions and data are not there in the CPU, then it has to wait, correct, yes or no, he has to wait. So how will I get rid of it? Because of caches. In the cache, when I fetch this previous instruction, because of principle of locality of reference, I would have fetched more instructions. When I fetch this previous data, again by principle of locality of reference, I would have fetched more data closer to it, and now based on spatial locality etc., he will be using that. So when he is pushed out and he is actually occupying the front side bus, this fellow will have reasonable amount of instructions to be executed in the cache and reasonable amount of data that instruction needs. Those things will already be in the cache, not by design but by actually the terminology that we had used, that we can afford to have this locality of reference. Okay. So if cache is not there, then this whole mission is a failure, right? When the cache is not there, then the whole mission is a failure, because cache gives you, so I put him there, the next fellow, and if he does not find any instruction or data, then he has to wait for the bus. The bus is now occupied by some other process. So P2 cannot compute its CPS unless the data and instruction that are necessary for P2 is already in the cache, and that our spatial locality, our block caches help, right? So block caches help. If I do not have block caches, then this whole concept of round robin scheduling would be an impossibility. So the three questions that we have answered, one thing is there is a need, there is a time quantum fixed, then one minute, then there is an interrupt that comes in, then from the timer, so a process is pulled out, another process is put in, the operating system essentially gets, the interrupt service routine is the scheduler, right? When the interrupt comes from the timer, it goes to interrupt service routine, right? That interrupt service routine is the scheduler. So that fellow takes care of pushing another process, and the CPU is not involved majorly in any IO operation, it is all done through DMA. And the last thing is that I need a block cache. If I do not have a block cache, the entire thing would be a failure. With these 4 points, we can install round robin. So to install round robin in a round robin scheduling in an environment involves these type of a discussion. Okay. Right.
Can two IO bursts happen at the same time?
Yes. Now we will talk about IO burst. See, he has already made that question. Now IO burst is nothing but some IO operation, and when two IO operation happens at the same time, then this whole bus gets clogged, right? So the way things have been designed now is that, let us take any IO peripheral. Okay, what is this one? So let us take any IO. The IO peripheral is split into three parts. One is the IO device itself, then there is called a device controller. It is a hardware, and then there is something called a device driver, which is a software. So handling a device is in three phases. There is a software which is a device driver, there is a hardware which is a device controller. The device driver programs this device controller to keep accessing the device and give values back. You are able to follow? So this is how thing. Now what has happened over a period of time, the device driver has to execute in the CPU. Well, then this is the bus, okay. So the device driver, what will be the execution of the device driver? Device driver will pass the necessary information to the device controller, like this hardware, this, that, everything, and then the device controller can start working, okay. Now these device controllers have become so powerful, right, that they can do lot of activities inside them. For example, you give the so they can do, say for example, if I take a graphics card, right, they can do the complete hidden surface elimination just like this, So these are all becoming sort of commodity products. Okay. So what happens is that the device controller essentially becomes much more powerful, so that when I want to do an IO activity, I do not pass lot of commands and data there. I give some simple command and then ask the device controller to basically execute it on all the systems that they are governing, right. So this is how this is how your IO burst is handled. So if I say I want to do lot of IO activity, the IO activity will not be perceived on the front side bus. Rather what you do is you give some instructions to the device controller saying this is one sample data and now you extrapolate and make the other data, something like that. Then the amount of traffic that will go on this bus will be tremendously reduced. Okay. So by making device controllers as yet another CPU, that is what happened, right. NVIDIA came out with a GPU, they actually wanted to make a CPU to start with, correct. So as and when my device controller starts maturing, essentially your overhead actually starts decreasing. Okay. Right. So this basically I tried to explain you the round robin scheduling and the notion of different things that come under, for example the cache, the DMA and the hardware timer. If all these things do not exist, then doing a round robin is impossible. Okay. Fair enough? Okay. So one of the things that we do is I pull him out, I push him in, right. How can this happen? This is called task switching. I move from one task to another task. Your fifth assignment essentially will be based on this task switching. Any doubts? No? Okay.